Good morning, everybody. Welcome to Zoom Monday version, and we'll continue our discussion of amines today. We are going to look at another instance where diazonium ions are useful, and that is towards the synthesis of diazonium dyes. That's a lot of dye in there. Diazonium dyes come from diazonium ions. We are familiar with aryl diazonium ions in that we've made them previously, and we saw that they were useful for conversion to things like phenols. If we warm this up in the presence of water, we would get a phenol. If we warm this up in the presence of potassium iodide, we would get an aryl iodide, etc. But here we're going to use them differently. We're going to react them as an electrophile towards a nucleophilic aromatic amine or ether. It says we're going to use some oxygen here for an ether, or even an alcohol would work, or an amine, and we're going to get a diazonium dye. And the mechanism will be explored here, and we'll get to review it at the end of this segment. Traditionally, you take nitrite ion and react it with hydrochloric acid, and we're about to make a nitrosyl cation for about the fourth time, I'm pretty sure. How does that happen? We protonate nitrite to make it into nitrous acid, and then we protonate the OH group on nitrous acid to make it a better leaving group, and we eliminate it with the lone pair on the nitrogen and on the oxygen attached to the nitrogen, and that generates a nitrosyl cation. We saw nitrosyl cations love reacting with things, and the particular things they love reacting with are amines. And we're going to do the same here. It's going to be an aromatic amine. It has to be a primary aryl amine. That means there's only one carbon attached, and that's the aromatic ring. This specific example, it's ortho amino benzoic acid, common name. Oh, I see a typo here. There should be an R here. Anthranylic acid. Anthranylic acid has nothing to do with anthrax. That's going to react as a nucleophile, and then tautomerization ensues, and then elimination. I'm going fast here because we've done this mechanism already. And you have your aryl diazonium ion as depicted in the middle here. It is ready for the addition of a nucleophile, a nucleophilic aromatic molecule such as N,N-diethylaniline. And that's going to be conjugate addition here, a conjugate nucleophile, I would say. It's resonating, and then it looks like the para position is what's reacting here. And that's exactly what happens. And this is the slow step. It's another version of electrophilic aromatic substitution. That was the most important reaction in the previous chapter. And here it is once again, also on the same test. The benzene attacks our electrophile. It's a super electrophile. And then we re-aromatize. Slow step here. Why is this the slow step? And then this would be the fast step. Good question. Slow because we're losing aromaticity. We've created an sp3 hybridized carbon atom here, which can't resonate in the circle that we require for aromaticity. So it would be quick to get rid of this species and make it aromatic again. Re-aromatization is what that's called. Re-aromatization. Slow step, we lose our aromaticity. And we've created methyl red. This picture of the molecules actually, this is the yellow form of methyl red. I know it sounds silly, but this is the conjugate base of the red form. And we'll discuss indicators and colors shortly. So we've made a diazonium dye. It's got 2 nitrogens in the middle. That's where the diazo comes from. Diazonium dye. I think somebody wants to mute their microphone right now. And there we go. And here are 3 diazonium dyes. Methyl red, the one we just learned how to make, is right here. Methyl orange, what's the difference between the two? Well, it looks like the same dimethyl aniline was used to make both. And we're going to outline that in our synthesis. But this one has a parasulfonate group. And this one has an ortho carboxylate group. And that causes the colors to be slightly different. Not as different as you would think. Here's an interesting molecule found in a lot of clothing, Trypan Blue. And what's it got going on? It looks like it's a diazonium dye on the left and on the right. And this is pretty common. And we're going to have to break it down and figure out how this thing was made. So we're supposed to outline syntheses of each of these dyes from a primary aryl amine. You might have to have a diamine or diamine. Yeah. And a nucleophilic aromatic species, and then give a complete mechanism for each step in the synthesis of methyl orange. So why don't we do that? Methyl orange. We have to decide which part of the dye started as an aniline, and that's the part that gets diazotized. It has to be some kind of aniline. This is aniline here. And let's look at this molecule. And since we're here, let's look at methyl red as an example. One of these pieces was an aniline, and the other piece was the nucleophile. The nucleophile is the easiest one to spot. Here it is. This is the nucleophile, a reminder. It's already here. And this is the electrophile here, the diazonium. Your nucleophile must have a phenol or phenol. I had put phenol and or together in one word, didn't I? The mind does play tricks. A phenol or ether or amine. And we do have the amine version here. You can't do this mechanism if you don't have an atom that can resonate towards benzene. I hope you see that a phenol can do that too. Just look at a phenol. In fact, we can make it generic right now and cover both the phenol and an ether. R equals H gives a phenol. R equals C gives an ether if that's a normal carbon and not a carbonyl. An ester would work here too, but I haven't seen too many dyes that have esters up there. So that's where we should start when we're given the product and we have to figure out which part was the nucleophile and which part was not. So start with the nucleophile. So think retro. Find the new. And I found it. New. And you'll see that's the exact molecule over here. And how do you know this wasn't the nucleophilic ring here? Is there a lone pair on this carbon? Heck no. If you don't have a lone pair, if it's not a phenol or an amine or an ether there, then that's not the part that was the nucleophile. It must be the other part. Okay, well, that helps. In the other part, the electrophile, we will then find E. And I found it. The rest. And the E in this case was here. Oh, formal charge. Which one of those nitrogens has a formal charge? The one on the left has 3 bonds and a lone pair. That's normal nitrogen. The one in the middle has 4 bonds. That's a cation. We call it a diazonium ion because there's 2 nitrogens in it. That's our electrophile. And what's it come from? You didn't start with that. It came from, if you look backwards, it came from this. Take a look. Where did we get the diazonium? Right there. We short formed this to AR, but this thing became a diazonium. So this NH2 ended up being an N here. We'll put a highlighter on it. This NH2 nitrogen was this one, the one attached to the aromatic ring. Where did this other nitrogen come from? We'll highlight it in a different color. And here we go. This one came from here, which is this one. And there it is all the way through. It's the nitrite ions, nitrogen. So I think we have all the pieces we need to outline the synthesis of methyl red. We have the nucleophile. It's here, I circled it. This thing came from the NH2 version of it right here. This is the other part of the molecule. And you'll see that was used in the synthesis right here. And so we got all the pieces we need. Let's outline our synthesis on the page after the next one. All right here. Outline the synthesis of each dye. We'll start with methyl red. And remember, we identified the nucleophile first. And that was the one that had a nitrogen with a lone pair on it. And then we identified the electrophile. And that broke down to, let's do methyl red. Try to come up with a fairly nice retro arrow here. Oh well. And our two pieces are this piece here and our other piece here. With a plus. And that piece is as is. You can circle it because that's one of the starting materials. Oh, it made it pretty. And this has to come from the aniline. Remember the diazonium dye comes from an aniline. Sorry, the diazonium electrophile. This is the diazonium dye. It's called methyl red. The diazonium electrophile comes from an NH2 here. Has to be NH2. Can't have groups on the nitrogen. And that's the other piece right there. And in terms of synthesis, you would have to show me how to go forwards. And as always, we can do it right here. How is that made into that? We're going to do that a lot on our test next week. You have to react it with NaNO2, HClAq, and you have to keep it cool. If you don't keep it cool, this water is going to react right here and put an OH instead of a diazonium ion. You'd have a phenol and you wouldn't get your methyl red synthesis. It's sad when that happens. We see it in the lab. And then you just have to mix these two together. Mix them together and finish off the synthesis of your diazonium dye. So let's show that. Yeah, purple's nice. You would just let those warm up. There are certain acid-base aspects to take into consideration when you're in the lab. For instance, when you're generating your diazonium dye, you are using a very acidic solution. And then when you introduce your amine, it protonates first with the HCl in solution. So you generally have to make things more neutral by adding a mild base at the stage after you've made this. But we're not going to worry about that. That's for the lab people to worry about. In lecture, we just make our diazonium species, react it with the appropriate nucleophile, and we make methyl red. Methyl orange, similar story. Let's see what we can steal. Yeah, I might have gotten a little too much, but that's okay. Just going to edit it. Methyl orange. I noticed they had very similar structures. So I don't think I'm going to have to tweak it too much. Methyl orange has the same dimethyl aniline portion on the left. So that portion of the analysis is identical. The amine on the right, the electrophile, diazonium electrophile, is this piece here, which is a little different. And we're just going to edit this thing. And my circle. Oh, I don't want to edit that one. That's the ones used for methyl red. I'm down here. I'm going to edit my circle, make it bigger, do some erasing. Can't erase the circle. And what was there in methyl orange? Methyl orange, ortho, oh sorry, para to the NH2 would be a sulfonic anion, sulfonate we call that. Sulfonate. We can ignore the spectator. It's SO3 negative. Isn't that an SO3 negative right there? Sure, SO, 3 O's and a negative. And congratulations, you made methyl orange. Where are we at? 820. Looks like we're going to do Trypan Blue, which you can think about during our short intermission. And we'll break it down. And it looks like this middle piece doesn't have a nucleophile in it. These are methyls. They don't have lone pairs on the carbon there. So the nucleophiles are out here and they look identical. So be thinking about this piece in the middle, doing something twice. And I will see you when we come back. We'll talk about Trypan Blue.